Okay, so today we're looking at differential equations, Euler's method, and logistic FRQs. Our first example is non-calculator. It says consider the differential equation given by the function for y does not equal 2. Let y equals f of x be the particular solution to the differential equation with the initial condition f of -1 equals -4. So the very first thing that they want us to do is evaluate dy dx, or the first derivative, and the second derivative at -1, -4. So the first derivative is straight up because they already gave me the first derivative in the problem. So I'm literally just plugging in the point -1, -4, simplifying this down, and I got 6. The second part, we have to take the second derivative. And remember, when you take the second derivative, every time you take the derivative of y, you need to include that dy dx. So that's usually the part that people forget. So the first part was just the 10x, and then when I took the derivative of the second part, which I used my memorize, I have to understand that that needed a dy dx on it because I took the derivative of y. Then I plug in my point, simplify that down, and I get -9. All right, so for this question, I get 1 point for evaluating at the first derivative, 1 point for writing out the second derivative, and then another point for doing the evaluation of the second derivative. All right, part B says, is it possible for the x-axis to be tangent to the graph at some point? And so a couple things I wanted to note. First, that the x-axis is the equation y equals 0, and the x-axis is horizontal, meaning that the slope is 0. So basically, I'm taking my derivative, and I'm putting in y equals 0, since I know that at the x-axis y is 0. Simplifying that out, I get 5x squared plus 3. And I do know that 5x squared, because that is something being squared, plus a number is always greater than 0. So that means the x-axis will never be tangent because it's never going to have a slope of 0. Right? It's always going to be greater than 0. All right, so I'm going to get 1 point for setting dy dx equal to 0 and y equal to 0, and then 1 point for my answer with my explanation. All right, so the next part, C, says find the second degree Taylor polynomial for f. Even though this is like a differential equations type problem, they can throw Taylor stuff in there as well. So to start, remember with your Taylors, you're going to walk your stuff out. Like you need f, f prime, f double prime, and so on. In this case, we'll stop at f double prime for the simple fact that they asked us for a second degree Taylor. So they gave me that f of -1 equals -4. And then we found earlier that the derivative at -1 was 6. And I found earlier that the second derivative at -1 was -9. So putting that all together and using my Taylor series format, I start with the -4, and then I have 6 x minus the center, or in this case x plus 1 to the first over 1 factorial, and then -9 x minus the center squared over 2 factorial. Remember, you do not want to put a dot on that. Second degree Taylor polynomial needs to stop at the second degree. All right, so from there, I just simplified it out to make it a little bit cuter. And I get 1 point for having a second degree Taylor polynomial, which is centered at -1, and then 1 point for getting my coefficients right, the -4, 6, and -9. All right, part C says use Euler's method starting at x equals -1 with 2 steps, or 2 equal steps to approximate f of 0. So with 2 equal steps, I'm going from -1 to -0.5 to 0. Show all the work that leads to your answer. Your table is your work. All right, so you're going to start that table off again. My x's are going to go from -1 to -0.5 to 0. When x is -1, y is -4. I know that slope was 6. Then I need to do my change in y. So I'm going to do 6 times my delta x, or 6 times a half, which is 3. And then I add that number to my old y, so -4 plus 3 is -1. And then I repeat those steps until I get my approximation of f of 0, and my approximation is that f of 0 approximately equals 5/8. So 1 point for using Euler's with 2 steps, and then 1 point for getting the right answer of 5/8. All right, the next question says the population is modeled by a function p, and it satisfies this logistic equation. Part A says, if the initial population is 3, what is the limit as t approaches infinity of p of t? Well, your limit of your function is going to go to your carrying capacity. Remember, you shouldn't go past your carrying capacity, and even if you do, you'll come back down to your carrying capacity. So really, no matter what p I'm starting with, it's still going to be my carrying capacity. In this case, this function is already written in a nice logistic form, so I can clearly see that my carrying capacity is 12. All right, then they ask, what about if you start at 20? Like, what if we start above the carrying capacity? Well, again, like I said before, even if I start above the carrying capacity, I'm still going to go back down towards the carrying capacity. Therefore, my limit is still going to be 12. So I'm going to get 1 point for each of those answers. All right, part B says if the population starts at 3, what value of P is the population growing the fastest? And so if you remember, your population is growing the fastest when it's half of the carrying capacity. So half of 12 is 6. For this one, I'm going to get 1 point just for the answer. All right, so it says a different population is modeled by the function y that satisfies a separable differential equation. Find yt if y0 equals 3. And so I rewrote this problem with y in it instead of p. And then I solve for y. I distribute my 1/5 back in. I literally integrated both sides. And then I plugged in my initial condition, and I got c equals 3. And then I put in that c value into my equation again. Lastly, to get rid of the ln, I e both sides, and I understand that the part with the ln3, that could really just come to the front. So again, they gave us this new differential equation, told us it was separable. I couldn't use a logistic equation because it's no longer logistic, it's just separable. All right, and your final answer should be some type of exponential. All right, so you get 1 point, which I love these problems. They give you so many points. 1 point for separating the variables, 1 point for the antiderivative, 1 point for the constant of integration, so your C. 1 point if you used your initial condition to find exactly what C is, and then 1 point if you actually solve for Y. All right, so if you had left it like L and Y, you would have lost that point. You have to actually solve for Y. All right, part D says for the function y found in part C, what is that limit? So we're doing the limit of what we found. I'm literally plugging in my infinity, and I'm understanding that the x squared or the t squared term is going to grow way faster than the t term. So that's going to trump the t term. And basically, I'm getting e to the negative infinity. I know that e to the negative infinity is just 0, so 3 times 0 is 0. Or you could have dropped the e like I'm showing here. Still understanding that that thing is going to, or my denominator now is going to infinity, so 3 over infinity is still 0. However you want it, however you want to do it, you should still get an answer of 0. So I'm getting 1 point for the answer there. Not much work. I didn't have to L'Hopital or anything like that, so just 1 point for the answer. All right, our next question says we have a cylindrical barrel with a diameter of 2 feet, contains rainwater as shown in the figure. The water drains out through a valve at the bottom of the barrel. The rate of change of the height of water in the barrel is given by this model, this differential equation, where h is measured in feet and t is measured in seconds. And then they were really kind because they gave us the volume of a cylinder. Now, keep in mind that I know in class I made you guys memorize all those volume formulas, but the harder formulas are the more uncommon formulas they generally give you on the AP exam, because they don't want you to get the question wrong just because you don't know your geometry. They're testing your calculus. They're not testing your geometry. Therefore, they'll often give you those formulas for volume and area, unless it's something basic like squares or rectangles. All right, so part A says find the rate of change of the volume of the water with respect to time when the water is 4 feet high. This sounds like a no find when type problem, so like a related rate. So I know that dHdt, they gave me this in the initial prompt, is -1/10 root h. They're asking me to find the volume, so dV dt, the rate of the volume, and then when the height is 4. All right, so I'm going to start with my volume formula, right, that I either knew or that they gave me. I'm also making a mental note that, hey, I know the radius is constant because it's a cylinder, right? So the radius is not changing because the circle of the cylinder base is never changing. And so if the cylinder had a diameter of 2, then now I know that I have a radius of 1, and I can actually plug that into the equation because it's not something that's changing. So that gives me a volume formula of pi h. From here, I'm going to go ahead and take my derivative, making sure I do like dv dt, dh dt every time I take a derivative of one of those values. I'm going to plug in what I know. And then I'm going to simplify it out. And when I simplify this out, I get -pi-fifths cubic feet per second. Make sure that you understand it's cubic feet because it's volume, per second because it's per time. They did ask for units, so you want to make sure you have your units on this problem. All right, so you're getting 1 for the dV dt equals pi dH dt. All right, so when the height of the water is 3 feet, the rate of change of the height of the water with respect to time, is it increasing or decreasing? So basically, they're asking about that rate of change of the rate. And so I have to find the second derivative. And so I took the first derivative, and then I took the derivative of that, making sure that I put dH dt every time I take the derivative of h. All right, so once I do that, I get a nice little equation. I have like -1/20 root h times that dH dt. And then I'm going to simplify that out, noticing that my root h's cancel. And so I'm left with 1/200. So since that number is greater than 0, the rate of change in the height is increasing when the height of the water is 3 feet. All right, so I see 1 point for having the -1/20 root h, 1 point for the second derivative, and 1 point for your answer with the explanation. All right, part C says at time t equals 0, the height of the water is 5 feet. So we're going to use separation of variables to find the expression. Again, anytime they ask you to use separation of variables, they're telling you to solve the differential equation, and it's usually a ton of points on the AP exam. It's really kind of cool because it's a really easy thing to do. So I'm going to start with my differential equation. I'm going to move the h to the other side. I'm going to integrate both sides. Plug in my initial condition. Once I plug in that initial condition, I get c equals 2 root 5. Plug that c back into the equation, divide it by 2, and then square it to solve for h. Again, I'm getting 1 point for separating properly, 1 point for the antiderivative, 1 point for the constant and using the initial condition, and then 1 point for getting my h.